So a lesson on gears then, and the first thing we need to do is to recap on what we did last time on levers. Levers and gears are very similar. You might not realize that, but hopefully you will by the end. So, as a bit of a starter, write down the formula to calculate moments, work out the moment of this 50 Newton force on a hammer of length 50 centimeters, and would it be easier or harder to remove the nail if the length of the hammer was increased? So the answer then, moments, force times perpendicular distance of the line of action from the pivot, 25 newtons, and it would be easier, this should say pivot, by the way, of the line of action from the pivot. So, three things that we're going to try to achieve in this lesson: describing the characteristic of gears, calculating the turning effect of gears, and the characteristics of gear systems with gear and turning effect ratios. So, looking at the characteristics of gears then. Well, a gear is really just a wheel and an axle, but the wheel has got teeth on it. So you have this wheel mounted on an axle. The axle would be going through here, and the wheel turns. The turning is passed on by the teeth that are on this gear and on the gear that it is turning. And by Newton's third law, you'll recall that if this wheel or this tooth exerts a force on that tooth, then that tooth exerts an equal and opposite force on this tooth. So the forces here on this tooth and the force on this tooth will be the same. And if you've been thinking about your physics, you'll realize that you're always looking for the things that are the same in your calculations. So, what gears do? They transfer rotational forces, they transfer power from one place to another, and so in that sense they are quite similar to levers. And you find gears all over the place, in cars and motorbikes, on ordinary bikes, in toys and watches, in tools, all over the place. Now the turning effect. Here we have an example of a gear, and the gear is either supplying a force here or having a force applied to it here, doesn't matter. But the turning effect, of course, is the force, size of the force, times the perpendicular distance of the line of action from the pivot. And the pivot, of course, is where the axle runs through. This is where the turning is happening around. So it is the size of the force times the radius of the gear. That's your turning effect for a gear formula. So, we have three tasks here, or three questions within this task. A gear of radius 20 mil, you should turn another gear of radius 10 mil with that force. What's the turning effect on the two wheels, the two gears? The turning effect of the force on a gear wheel of 40 mil radius should always be less than 4.8 Newton meters. Calculate the maximum force on the gear wheel to stay within the 4.8 Newton meters. And finally then, a gear of radius 96 centimeters, turning a smaller gear of radius 16 centimeters. The turning effect of the larger gear is 120 Newton meters. What's the resultant turning effect of the smaller gear? So, 4 calculations, possibly 5 minutes, and you have the formula at the bottom there to help you. Do them, having paused the video, and then restart to see the answers. So, with the 10 mil wheel, you've got 80 newtons times 10 mil gives you 800 Newton millimeters. That's not a standard unit, so it's 0.8 Newton meters. 20 millimeter wheel, 80 times 20, 1600 Newton millimeters. See the pattern there? we have doubled the radius, we have doubled the turning effect. That's not a random thing. Question 2, well, you've got 4.8 Newton meters and you've got 40 mil, so we divide that by 1,000 to get it into meters, times F. So F, then rearranging that formula, we are multiplying both sides by 1,000, 4.8 times 1,000. Then we are dividing both sides by 40, 4.8 times 1,000 divided by 40 to get just F on this side. And if we evaluate that, we get 120 newtons. Notice there should always be units. Question 3 then. 120 Newton meters means that the force on the teeth of the 96 centimeter gear is 120 divided by 0.96. Again, we're doing this in meters. Our torque, our turning effect, is in Newton meters, so we convert our centimeters into meters, and we get 125 newtons. This then is the force that's acting on the smaller gear, and the turning effect is the size of the force times the radius of the gear, 125 times 0.16 again in meters to get 20 Newton meters. Hopefully that's all nice and clear. Do review that if you're not sure, so that you are sure about those calculations. Final aspect of the work then, being able to explain the characteristics of gear systems and calculate gear and turning effect ratios. So here we have two gears. The input gear in red is turning clockwise, and hopefully you can see, without me telling you, that the output gear is turning anti-clockwise. So one of the things we can do with gears, apart from changing the turning effect, apart from changing the speed of rotation, we can also change the direction of rotation. So our engine might be driving in the clockwise direction, but we want the car to go backwards, and so we arrange it maybe like this. If we had a third gear then, hopefully you can see that the third gear would be turning clockwise just like the first. You would go clockwise, anti-clockwise, clockwise, because each gear reverses the direction of the rotation from the last. So, two interlocking gears, different sizes. Hopefully you can see that the large gear is turning more slowly than the small gear. So the smaller gear is turning faster, but it has a smaller turning effect. Remember, the force here and here is the same. So if you've got the same force acting on each of the teeth that are touching, but this has a smaller radius, the turning effect over here of that force will be less than the turning effect of the force over here. So you're not getting something for nothing, and you never do. If you think about your lever, you could apply a smaller force to the lever to lift a heavy load, but in order to do that, you had to move your point of application further than you actually lifted the load. So the same work is being done at best, and you are choosing to do that work with a smaller force, and so you have to travel further. Same idea here. So this is a speed multiplier system. Here then, we have an input 12-tooth gear to an output 36-tooth gear. And you can see, apart from the fact that the direction of rotation is reversed, you can see that the 36-tooth gear is turning much more slowly. If you were to look carefully, you would see that the 36-tooth gear is turning at 1/3 of the rate of the 12-tooth, or the 12-tooth gear is turning 3 times faster than the 36-tooth gear. But again, remembering that the forces being applied by one tooth to the other when they touch is the same, there's a much greater turning effect with the 36-tooth gear. So even though it's traveling more slowly, it has a bigger turning effect. So this is a turning effect multiplier. So a summary of what gears can do. They can transfer rotational power, they can change the rotational direction, they can change the output speed, they can change the turning effect. The two ratios that we were talking about at the start, the gear ratio is the output over the input, and that could be the output number of teeth over the input number of teeth, the output radius over the input radius, the output diameter over the input diameter. And the gear ratio is also the turning effect ratio. So they're the same thing. So a 540mm gear, turning effect 120, what's the turning effect on the 360? You should be able to work that out. Here we have three tasks again. The third one is to do with the questions that I had set separately. So for the above gear system, state what happens to the resultant speed and turning effect of the larger output gear compared to the smaller one. If the 2 centimeter gear has a turning effect of 6 Newton meters, calculate the turning effect on the 10 centimeter gear. And then those 4 questions that I have set separately. So do those 2 now, maybe 3-4 minutes, and then having paused the video to do that, restart the video, and the answers come up afterwards. So if you have an arrangement as shown, the turning effect will be larger, but the speed will be smaller. If the 2 centimeter gear has a turning effect of 6 Newton meters, the turning effect on the 10 centimeter gear, well, 6 Newton meters means the force would be 6 divided by 0.02, that is 2 centimeters in meters, which gives you 300 newtons. That's the force then acting on the larger gear. 300 times the radius of that larger gear, 0.1 meters, 30 Newton meters. Finally then, 9 questions to check your understanding of the knowledge that we have been discussing today. Once you're happy you have the answers, there they are.